Multi-objective optimization of process parameters on MRR and TWR in EDM for N353 material using Grey-Taguchi method. Abstract: the use of the Taguchi method with Grey relational analysis to establish the process parameters in electro-discharge machining of N353 alloy steel with selected tool electrode material. Throughout the study, multiple quality characteristics like tool wear rate, TWR, and metal removal rate, MRR, are focused. The effort has been made to minimize tool wear rate and maximize metal removal rate to produce high-quality finishing of the die. The process parameters, namely peak current, pulse on time, different tool materials are optimized with respect to tool wear rate and metal removal rate, using the Taguchi quality design concept. An L9 orthogonal array table is chosen for the experiments. From the Grey analysis, a Grey relational grade is obtained, and based on this value, an optimum level of process parameters has been identified. Furthermore, using analysis of variance method, significant contributions of process parameters have been determined. The results of the confirmation experiment show that the optimal process parameters may be determined successfully so as to perk up numerous quality characteristics, TWR and MRR, through this approach. Keywords: EDM, electrode, pulse on time, MRR, TWR. Introduction. Electrical discharge machining process, which is also called electro-erosion machining process. When the gap voltage is sufficiently large, i.e. reaches the breakdown voltage of dielectric fluid, high power spark is produced, which increase the temperature about 10,000 degrees Celsius. By this way the metal is removed from the workpiece. A major advantage of EDM is that the tool and the workpiece do not come into contact too. In this process material is removed by controlled erosion through a series of electric sparks between the tool, electrode, and the workpiece. The thermal energy of the sparks leads to intense heat conditions on the workpiece, causing melting and vaporizing of workpiece material. Due to the high temperature of the sparks, not only work material is melted and vaporized, but the electrode material is also melted and vaporized, which is known as electrode wear, EU. The EU process is quite similar to the material removal mechanism, as the electrode and the workpiece are considered as a set of electrodes in EDM. Due to this wear, electrodes lose their dimensions, resulting in inaccuracy of the cavities formed. During EDM, the main output parameters are the material removal rate, MRR, and tool wear ratio, TWR. Electric discharge machining, EDM, is a non-traditional machining operating procedure in the manufacture of complex shaped dies, molds and scathing parts used in automobile, aerospace, surgical and other industrial applications. Electrical discharge machining, EDM, is extensively used for high-strength materials. An analysis on the influence of current, pulse duration and duty cycle over MRR and TWR was performed. EDM is now unquestionably recognized as an important precision machine tool forming process for producing internal shapes on workpiece. This study presents experimental analysis based on 3 factors and 3 levels orthogonal array L9 design. The objective of this research is to study the performance of different electrode materials on N353 workpiece with EDM process. N353 is a high-feature alloy steel giving good ductility and shock-resisting properties collective with resistance to wear. This steel is mostly known as bearing steel and used for bearing production in industrial sector. N353 steel is chiefly famous as bearing steel. This is used for roller bearing components such as 1, brakes 2, cylinders 3, conical and needle rollers. Studies show that selection of process parameters and fixing the appropriate range of parameters to machine every product decides the quality of the product and in turn the process's requirements. Vikas et al. Has done EDM process optimization with multiple performance characteristics based on orthogonal array with Grey relational analysis for N41 with copper electrode 4. Shaleshtawanganet al. Studied the process of EDM with cylindrical shaped graphite tool electrode and AISIP20 workpiece for obtaining favorable preference measures in surface integrity, surface crack density, white layer thickness and surface roughness. using PCA-based Gray relational analysis has been selected 5. The original Taguchi method was designed to optimize only a single performance characteristic, whereas the Gray relational analysis has been proved to effectively resolve the complicated interrelationships among multiple performance characteristics of the EDM process. The goal of the present study was to determine the optimal machining parameters for maximum MRR and minimum TWR under given machining conditions. The Taguchi method was employed to explain the effect of the machining parameters on the characteristics of the EDM process. Additionally, Gray relational analysis was used to find the optimal machining parameters satisfying the multiple characteristics of the EDM process. 2. Experimental details. A. Tool material. In EDM, electrode material plays a significant role. During study, the electrode material is measured as a variable. In the present study, 3 different electrodes are used as tool material for machining. The electrode materials used are brass, aluminum, and copper. B. Work material. In the present study, the work material N353 is used, whose hardness is 62 to 64 HRC, and figure 1. Shows that the work piece before and after the machining. 3. Research methodology. The selection of optimum machining parameters in EDM is an important step. Taguchi optimization technique is single parameter optimization based on the signal-to-noise ratio 8. Gray relational analysis is applied to optimize the parameters having multi-responses through Gray relational grade. Furthermore, a statistical analysis of variance, ANOVA, is performed to see which process parameters are statistically significant. The steps involved are: A. Selection of process parameters and RESP1s. The process parameters and levels chosen for the experiments are shown in the table I. These parameters are so selected because of the prominent impact on the performance and at the same time may be controllable individually and effectively. B. Design of experiment. Experiments are performed, randomly, according to the L9 orthogonal array generated by Minitab 17 software, on N353. For each experiment a separate electrode is used. The machining time is 10 minutes for all experiments. The machining time is noted from the timer of the machine. The electrode wear rate is calculated by weight difference of the electrodes using automatic weighing machine with 300 G capacity with a precision of 10 milligrams. The experiments along with the details of the values of various parameters for evaluating TWR MRR based on L9 orthogonal array are shown in Table 2. 4. Result and discussion. A. Observation and calculation for MRR and TWR. After the experimental procedure, different response factors like MRR, TWR calculated from the observed data in Table 3. Statistical analyses were performed on the calculated values, and the where is the value of the response, S.No is the experiment condition with number 1, 2, and 3, n. B. Calculation for normalized value of S/n ratio. In this step of the Gray relational analysis, pre-processing of the data was first performed for normalizing the raw data for analysis. This is shown in Table 4. She is normalized by the following formula to avoid the effect of adopting different units and to reduce the variability. The normalized output parameter, MRR, corresponding to the larger the better criterion can be expressed by equation 1 and 2. C. Calculation for deviation sequence. The Gray relational coefficient is calculated to express the relationship between the ideal, best, and actual normalized experimental results. Before that, the deviation sequence for the reference and comparability sequence were found out. These are given in Table V and Gray relational coefficient is given in Table 6. The deviation sequence can be expressed by equation 3. D. Calculation for Gray relational coefficient and grade. After data pre-processing is carried out, a Gray relational coefficient can be calculated with the pre-processed sequence. It expresses the relationship between the ideal and actual normalized experimental results. The Gray relational coefficient is defined as follows by equation 4. Where k is the deviation sequence of the reference sequence x, k, and the comparability sequence is 11, k. Distinguishing or identification coefficient. If all the parameters are given equal preference and taken as 0.5. The Gray relational coefficient for each experiment of the L9 OA can be calculated using equation and same is expressed in Table 6. After obtaining the Gray relational coefficient, the Gray relational grade is computed by averaging the Gray relational coefficient corresponding to each performance characteristic. The overall evaluation of the multiple performance characteristics is based on the Gray relational grade that is given by Equation 5. Where if the Gray relational grade for the ith experiment and n is the number of performance characteristics which is taken as 2 for MRR and TWR, Table 6 shows the Gray relational grade for each experiment using L9 OA. The higher Gray relational grade represents that the corresponding experimental results is closer to the ideally normalized value. Experiment 7 has been multiple performance characteristics among 9 experiments because it has the highest Gray relational grade. It can be seen that in the present study, the optimization of the complicated multiple performance characteristics of EDM of N353 has been converted into optimization of a Gray relational grade. Calculation for main effect and ANOVA. Since the experimental design is orthogonal, it is then possible to separate out the effect of each machining parameter on the Gray relational grade at different levels. 1, 2, and 3 can be calculated by averaging the Gray relational grade for the experiment 1 to 3, 4 to 6 and 7 to 9 as respectively as shown in Table 8. The mean of the Gray relational grade for each level of the other machining parameters, namely duty cycle, peak current, pulse on time and tool material, can be computed in the same manner. The mean of the Gray relational grade for each level of the machining parameters is summarized and shown in Table 7. In addition, the total mean of the Gray relational grade for the 9 experiments is also calculated and presented in Fig. 2. Shows the Gray relational grade obtained for different process parameters. The mean of Gray relational grade for each parameter is shown by horizontal line. Basically, the larger the Gray relation grade is, the closer will be the product quality to the ideal value. Thus, larger Gray relational grade is desired for optimum performance. Therefore, the optimal parameters setting for better MRR and lesser TWR are A1B1C3, as presented in Table 7. Optimal level of the process parameters is the level with the highest Gray relational grade. Furthermore, ANOVA has been performed on Gray relational grade to obtain contribution of each process parameter affecting the 2 process characteristics jointly and is discussed in the forthcoming section. ANOVA for Gray relational grade is presented in Table 8. Percentage contributions for each term affecting Gray relational grade are shown in Fig. 3. Fig. 3 clearly shows that tool material is the dominant parameter that affects Gray relational grade and hence contributes in improving MRR and reducing TWR. It can be seen from Figures 2 and 3 that current is the most significant factor that affects the Gray relational grade. Metal removal is directly proportional to the amount of energy applied by the current. Confirmation test. Confirmation test has been carried out to verify the improvement of performance characteristics, MRR and TWR, in N353 using EDM. The optimum parameters are selected for confirmation test as represent in Table 9. Table X, which shows the comparison of the experimental results using the initial orthogonal array A1B3C3 and optimal, Gray theory prediction design, A1B1C3, machining parameters. Based on table, MRR is accelerated from 0.430 to 0.4863 g/min, the TWR is decreased from 0.0213 to 0.0158 g/min. The corresponding improvements in MRR and TWR are 13.09% and 25.82% respectively. It is clearly shown that the multiple performance characteristics in the EDM process are greatly enhanced through this study. 6. Conclusion. The GRA based on the Taguchi method's response table has been proposed as a way of studying the optimization of EDM process parameters for N353. The optimal machining parameters have been determined by the Gray relational grade for multi-performance characteristics that are MRR and TWR. 9 experimental runs based on OAs have been performed. The following conclusions can be drawn from this study. 1. The work has successfully evaluated the feasibility of EDM of N353. 2. From the response table 9 of the average Gray relational grade, it is found that the largest value of Gray relational grade for tool material, peak current and pulse on time are copper, 5A and 50S respectively. These are the recommended levels of controllable process factors when better MRR and lesser tau is simultaneously obtained. 3. The ANOVA of Gray relational grade for multi-performance characteristics reveals that the tool material and peak current are the most significant parameter. 4. Based on the confirmation test, the improvements in MRR and TWR are 13.09% and 25.82% respectively. It is shown that the performance characteristics of the EDM process such as MRR and TWR are improved together by using the method proposed by the study. The effectiveness of this approach has been successfully established by validation experiment.